Today, we're going to go through the details of an evaporation process. In front of us, there are 4 flasks. There are actually 3, but I added another one on the left. These 4 flasks represents the 4 different stages of one evaporation experiment. So what I'm going to do is I'm going to talk through this experiment. You make sure stay with me, follow me. So this evaporation experiment starts like this. Initially, I'm going to add some liquid into a flask. Let's assume the liquid is water. So we're going to add some water into the flask. We are looking at the first one right now. After we add water, assume we can do this. No one can do this, but let's assume we can. What we can do, let's assume we can pump out everything in this area. All the air was pumped out, nothing here. Then we cap the flask, sealed. Then that time is recorded as time 0. At time 0, there is liquid water in the flask. Above the liquid, it is a vacuum. There's nothing. Make sense to you? But right at that moment, since there's nothing in the vacuum in the above area, above space of the water, what will happen is that some of the water molecules on the surface of the water liquid will start evaporate. At that moment, the only thing that is happening in the flask is evaporation. Well, if you are sitting here, observe that flask while evaporation is going on. What can you observe? You will observe the surface of the liquid start to drop. It goes below the original mark. Does that make sense to you? Now let's assume we passed the initial t time 0 moment. We come to stage A. In stage A, now there are a few particles in the space above the liquid. Now there are actually 2 processes going on inside the flask. Number 1, evaporation. Some molecules on the surface of water will keep evaporating. Number 2, some of these particles in the space above the liquid may dive right back to the liquid to become a part of liquid condensation. So there are 2 processes going on now. Right past time 0, there will be 2 processes going on inside the flask: evaporation and condensation. We can imagine at the beginning, at the early stage of the experiment, the evaporation will be way faster than condensation because there aren't a lot of particles in the gas state in this space above the liquid. There aren't lots of gas particles, only a few. So at that moment, in the case of A, evaporation is way faster than condensation. What you observe, if you're sitting, you cannot see those particles evaporated or condensed. What you can see is that the surface of the liquid keeps dropping. Does it make sense to you? As long as the surface of the liquid keeps dropping, you know evaporation is faster than condensation. So in flask A, the liquid level still keeps dropping as molecule evaporates. Well, given some time, we move to stage B. Now, still 2 processes are going on: evaporation and condensation. So there are 2 processes going on. But we know along with time, while more and more water molecules go into the gas state, condensation is becoming faster and faster. There are more gas particles may dive back into the liquid water. Make sense to you? So along with time, condensation will pick up speed. Well, How do you know it is becoming faster and faster? Again, you cannot see the condensation, you cannot see the evaporation. What you can see is that surface of liquid still keeps dropping. However, you know along with time, the rate of the surface dropping is becoming slower and slower. Does that make sense to you? So in flask A, the surface dropping rate is a lot slower than in the stage A. So the drop in stage B, the drop of liquid level slows down. Still, evaporation is greater than condensation. As long as you see surface of the liquid drops, you know evaporation is still faster. Now, given enough time, we know eventually we're going to go to the stage labeled as flask C. Now, sitting in front of this class, you sit there forever, you watch it, the surface of the liquid will stop dropping. It will stay there forever. At this moment, we know the rate of evaporation equals the rate of condensation now. Make sense to you? So this whole thing, we didn't do the experiment, but we described the whole process of this experiment. Now, let's focus on flask C, where there is no net change anymore. You cannot observe any change in flask C. However, you do know evaporation and condensation are still going on. They're just happening at an equal rate. So let's focus on flask C. Let's see what we can conclude from here. The rate of evaporation equals the rate of condensation. These are two opposite processes. When they equal, when there are two opposite processes are happening at an equal rate, we say the system is in the equilibrium. We'll come back to talk about equilibrium again. So in flask C, we say the system is in the equilibrium. Also, the pressure exerted by the vapor here in flask C is at its maximum. It is way greater. It is greater than there. It is greater than there. Does that make sense to you? Because at the equilibrium, you have the maximum of amount of gas particles there. You cannot go beyond that. Goes beyond that, condensation will become faster. It will be faster than the evaporation, so it will condense back. So at the equilibrium, there are the maximum amount of gas particles above the liquid, okay, in the space above the liquid. So we know if you have the maximum amount of gas, then the pressure exerted by the vapor at its maximum right now. This pressure, the pressure exerted by the vapor in the flask C, where the condensation and the evaporation are in the equilibrium, that pressure is called the vapor pressure. Okay, we come back, look at, now we only focus on flask C. This is what we had on the last slide. Rate of evaporation equals rate of condensation. We say that the system is in the equilibrium. Well, let's look at the definition of an equilibrium. An equilibrium is a condition in which two opposite processes take place at the same rate. Okay, in this case, evaporation and condensation. Equilibrium could be physical or chemical. Right now, we're describing a physical equilibrium. Both processes are physical changes. In the later part of this semester, we're going to talk about chemical equilibrium, where reactions are going back and forth. Chemical reactions. At the equilibrium, there is no net change can be observed. However, the system is called dynamic. All equilibria are dynamic. Dynamic means there are still something going on. They never stop. So all equilibria are dynamic processes. Like I said, equilibrium can be chemical or physical. Right now, the equilibrium we are talking about here is a physical equilibrium. Now let's look at the second conclusion we had in flask C on slide number 1. Okay, the pressure exerted by the vapor is at its maximum for the liquid at a given temperature. That pressure is called vapor pressure. Now, here's the definition of vapor pressure. Pressure exerted by a vapor above a liquid when the liquid and the vapor are in equilibrium. Well, liquid and the vapor are in equilibrium. It means that the evaporation and the condensation are in equilibrium. That is called the vapor pressure of this liquid, in this case water, of this liquid at this temperature. Okay, the vapor pressure is the maximum pressure evaporation can make at that temperature for that liquid. Again, the vapor pressure is the maximum pressure for the vapor of a liquid can reach at a given temperature. Well, how much you can get? What will be the value of a vapor pressure? The magnitude of vapor pressure depends on the nature of the liquid and the temperature of the liquid. So two factors decide what eventually in flask C, what the pressure can reach. It's decided by the nature of the liquid. Different liquids may have different vapor pressure, and also depends on the temperature. Same liquid at different temperatures, they will have different vapor pressures. So we're going to talk about this in details. We're going to talk about the temperature first. Well, let's assume we do two experiments in parallel. We use the same liquid. Both experiments we use water. The first one is done at room temperature. The second one is done at, let's say, 80 degrees Celsius, higher temperature. We know eventually when both systems reaches the equilibrium, in the experiment that is done at 80 degrees Celsius, guaranteed there will be a lot more particles here. The pressure here will be way higher than the one done at a lower temperature. Does that make sense to you? Why is that? Because for liquids to evaporate, they need to have higher kinetic energy. The higher the kinetic energy, the faster the evaporation. So when the experiment is done at a higher temperature, those liquid molecules has way higher kinetic energy than the one that was done at a lower temperature. So they evaporate faster, they evaporate easily. Eventually, they will have a lot more particles above the liquid, in the space above the liquid. They need a lot more particles to condense back to equilibrate with the rate of evaporation, which is faster at a higher temperature. As a result, higher temperature, higher vapor pressure. So if you do two experiments with the same liquid in parallel, and you can measure the pressure eventually in flask C for each one, the one that's done at a higher temperature, the pressure in flask C will be higher than the one that is done at a lower temperature. So higher temperature, higher vapor pressure. All right, we just covered the temperature impact on the vapor pressure. Now let's look at the nature of the liquid. Let's consider, again, two different evaporation experiments, but using two different liquids. One is water, like we did. The other, let's say, gasoline, a substance that evaporates easily. If you do this one by the end of the experiment in the flask C, in each case, which one do you think the pressure will be higher? Of course, gasoline. Gasoline, we know it evaporates way easier than water. When we say it evaporates easier, we mean it evaporates faster than water. It evaporates faster than water. Eventually, you need more particles in the space above in flask C to equilibrate with the faster uh, uh, evaporation. You need lots of molecules to condense to equilibrate with the evaporation. So the one for the gasoline molecules, in that experiment, the vapor pressure is higher. Now we see different liquids will have different vapor pressure. But why do gasolines, what kind of molecules will have a higher vapor pressure? Okay, remember in the last episode when we talked about evaporation, we concluded that for molecules to evaporate, they need to gain enough kinetic energy to overcome the attractive force among the liquid molecules. Do you remember that? All right. So the reason gasoline molecules evaporate faster is because the attractive force among the gasoline molecules are weaker than the attractive force between water molecules. So gasoline molecules do not need a lot of kinetic energy to overcome the attractive force. Well, in the case of water, molecules are tightly attracted together to each other, so you need a lot of kinetic energy to overcome that. Not a lot of molecules have that much kinetic energy, so it evaporates slowly. So liquids that have strong attractive forces between molecules, when you have strong attractive forces between molecules, it is hard to evaporate. Those kind of liquids, the liquids that are hard to evaporate, will have lower vapor pressure than the liquids that have weak attractive force between the molecules. So eventually, in the experiment with gasoline, the vapor pressure will be higher. Substances that have high vapor pressures evaporate readily. Make sense? Gasoline has a higher vapor pressure than water. We can know from the experiment, if we do those two parallel experiments, we will see gasoline has a higher vapor pressure. Now, the conclusion is that substances with high vapor pressure evaporate readily. Then here comes the definition of volatile substance, a substance that readily evaporates at room temperature because of a high vapor pressure. Volatile substances have high vapor pressure. We basically completed this episode. However, before we're done, I would like to emphasize again the three new or relatively new concepts we just covered. I would like to emphasize the relationship between the three. They are always linked together. A volatile substance is a substance. A volatile substance is a substance that has weak attractive force between molecules that has high vapor pressure. When the molecules are attracted together by weak forces, then it is easier to evaporate them. That's why they're volatile. When a substance is volatile, the vapor pressure will be very high. It will generate a lot of vapor. So vapor pressure will be high. Volatile substance, weak attractive force between molecules, high vapor pressure. Well, the so-called attractive forces between molecules is actually called intermolecular forces. We haven't learned what they are yet. We will learn them very soon. So now try to relate the three concepts like this. volatile substances, weak intermolecular forces, high vapor pressure. Try to memorize and understand this relationship among the three concepts. See you next time.